So glycolysis has 10 overall steps. This is where we left off last time. We're going to look at those 10 steps, and we're going to focus on the first 5 for this presentation. So during the preparatory phase, what we really see is the conversion of glucose via hexokinase to glucose 6-phosphate. We then see an isomerization reaction where we move the phosphate and create fructose 6-phosphate. And then we add a second phosphate to form fructose 1,6-bisphosphate, expending some ATP in the process. And then we use aldolase to cleave our fructose 1,6-bisphosphate to form glyceraldehyde 3-phosphate. In the payoff phase, we actually convert our glyceraldehyde 3-phosphate and dihydroxyacetone phosphate into all glyceraldehyde 3-phosphate. We then do an oxidation reduction reaction to generate 1,3-bisphosphoglycerate. Then from there, we're going to take a look at a phosphorylation, another isomerization, the formation of an enol, and then generating pyruvate from phosphoenol pyruvate. So that's going to be where we're going today. Here's the logic that we can think about in terms of glycolysis. So this shows, right, not so much the structure, but really the change that's occurring in this case. If I take a look at step 1, this is the phosphorylation of glucose. So this is where I use hexokinase and magnesium ions in addition to ATP to generate a phosphoester bond. Notice this delta G is negative, so this reaction is favorable. It's one of the irreversible steps in glycolysis. So the idea here is that this is what traps glucose inside the cell. It lowers the intracellular glucose concentration so that more glucose can be taken up. It actually uses the energy of ATP. In eukaryotes, this takes place using the enzyme hexokinase. In prokaryotes, it's the enzyme glucokinase. Of course, the nucleophilic oxygen at C6 of the glucose attacks the last gamma phosphate of ATP. And then it's the ATP-bound magnesium 2+ ions that facilitates this process by shielding the negative charges on ATP. So this reaction, again, is highly thermodynamically favorable or irreversible. It's regulated mainly by substrate inhibition. If I look at step 2, this is the phosphohexose isomerization. So this is converting glucose 6-phosphate to fructose 6-phosphate. Again, this has a positive delta G. The rationale here is that the C1 of fructose is easier to phosphorylate by PFK. This allows for symmetrical cleavage by aldolase. And, right, in aldose, glucose can isomerize to a ketose, such as fructose, via an enediol intermediate. So this isomerization is catalyzed by the active site glutamate via general acid-base catalysis. Now, of course, this is slightly thermodynamically unfavorable or reversible. So as long as product concentration is kept low, this reaction drives forward. You can actually see the mechanism here of the isomerization reaction and the formation of the enediol to generate the fructose. This is base catalysis. So I have binding and opening of the ring. I then have proton abstraction that leads to the formation of the cis-enediol. And then I form my fructose 6-phosphate. Now in step 3, I'm actually priming for phosphorylation. So here I take my fructose 6-phosphate and I add another phosphate via ATP to form fructose 1,6-bisphosphate. And again, notice this has a high negative delta G. So the rationale here is that this is further activation of glucose. This allows for 1 phosphate per 3-carbon sugar. And it's the first committed step of glycolysis. So fructose 1,6-bisphosphate is committed to become pyruvate then and yield energy. This process uses the energy of ATP. Again, it's highly thermodynamically favorable or irreversible. This phosphofructokinase 1 is highly regulated. So it's regulated by ATP as well as fructose 2,6-bisphosphate and other metabolites. Right? If there's lots of ATP, then we don't force the glucose through. Step 4 is the aldol cleavage of fructose 1,6-bisphosphate. And aldolase is what accomplishes this. Notice I form 2 products, the dihydroxyacetone phosphate as well as the glyceraldehyde 3-phosphate. Notice the positive delta G. So the rationale here is that it's cleavage of a 6-carbon sugar into two 3-carbon sugars. It's the high-energy phosphate sugars that are the 3-carbon sugars. The reverse process is the familiar aldol condensation. So most animal and plant aldolases employ covalent catalysis, whereas fungal and bacterial aldolases employ metal ion catalysis. This is a thermodynamically unfavorable or reversible reaction, and so it's the glyceraldehyde phosphate concentration that's kept low to pull the reaction forward. So these are class 1 aldolases. You can see the mechanism here in terms of that transfer, the formation of a Schiff base, the proton exchange, the hydrolysis of the Schiff base, and then isomerization, ultimately leading to the products. If you wanted to look at that in a little bit more detail, you have the binding and opening of the ring. You have a lysine that attacks the substrate carbonyl, leading to the formation of some type of tetrahedral intermediate. You then have the formation of a Schiff base on the enzyme, so the electrons are delocalized. Then you have carbon-carbon bond cleavage, which is the reverse of the aldol condensation. Then you have isomerization, so going from the protonated Schiff base to some type of covalent enzyme enamine intermediate. And you have proton exchange with the solution that restores the enzyme, and then your Schiff base is hydrolyzed in the reverse of the Schiff base formation. In step 5, we see the conversion of dihydroxyacetone phosphate to glyceraldehyde 3-phosphate through, again, an isomerization reaction. Again, this delta G is positive, 7.5 kilojoules per mole. So this is what allows glycolysis to proceed via one pathway. Aldolase creates 2 triose phosphates, the dihydroxyacetone phosphate and the glyceraldehyde 3-phosphate. Only the glyceraldehyde phosphate is the substrate for the next enzyme. The dihydroxyacetone must be converted to the glyceraldehyde 3-phosphate, and this is what completes the preparatory phase. And again, this is a thermodynamically unfavorable or reversible reaction, so the glyceraldehyde 3-phosphate concentration is what's kept low in order to pull the reaction forward. So we're going to stop there today, and we'll pick it up next time. Thanks.